There are 5 basic types of forces that we will be using in this unit. The first one is the gravitational force. It's the force that pulls everything downward. Every object with mass pulls it downward towards the center of the Earth, for example. And we will usually label the gravitational force as mg. And we will see why when we do some problems. The gravitational force applies to anything with mass that is sitting in a gravitational field. The Earth has a gravitational field, and pretty much anything with mass will have a gravitational force on it. By the way, so we label it as mg. You may see it as F, capital F with a subscript g, but in this class, you'll pretty much see mg the most. Lowercase m, lowercase g. Um, the gravitational force always, and I mean always, in this class, points straight downward. Gravity will never push you up on this planet, won't push you to the side. And yeah, it points you towards the, or points straight downwards towards the center of the Earth. Um, okay. The next force is kind of a strange force, meaning most people have a hard time thinking of this one. But of course, it's called the normal force. So I'll kind of show you what that means. The normal force, we will label it as capital F subscript capital N, but you might see it labeled as N sometimes. And this is what a normal force is. So I'll just draw another one here. Let's say you have a cup of coffee. Tried my best there. And it's sitting on a table. Shouldn't have drawn it 3D, but here we go. Here's the table. Gravity is pulling the cup downward, and kind of don't want to get in the habit of doing this, but gravity is pulling downward on the cup with a force mg. But if that were the only force on the cup, it would be in free fall. It's not in free fall. The table is pushing back up against it. So there's an upward force on the cup, which we will call the normal force. It's just a contact force from a surface, and the surface of this table is like this. The force, the normal force, is perpendicular with it, so we say it is always perpendicular to a surface, okay? Most of the time it will be some object sitting on the surface, and so the normal force just kind of points up, perpendicular to that surface. So that we'll see this a lot. Might be a stapler, it might be a typewriter, it might be a cup or something that's sitting on a table. The table pushes upward on it with a force Fn. Friction force. We'll call that F. Let's call it FF. Capital F with a subscript capital F. Is that true? Sometimes we show it like that, I believe. It all depends on what I want to do this year. I think I'll do capital F, lowercase f. Capital F for the force and lowercase f meaning friction. Okay, so let's take that same mug. I'll just move it down here. Don't need it up there anymore. And let's clean this up. Whoops, that's too much. We'll redo this. There. So, I want you to imagine you take your hand and I guess that's the best color I have there. And you push. You push on the cup and you start pushing it to the left. Okay, so we put a force on this to the left. Depending on the two surfaces involved, the cup and the table, there's usually some friction there. And friction opposes slipping. In this case, there will be friction on the cup, which opposes this motion. This is not always true though. But when we push on the cup, there is friction pushing back against us. And so it is a contact force from the surface, but it is always parallel to the surface. So if the surface is this way, the friction force is parallel with it. Cool. And it just opposes slipping. Here's another example. I think I'll just give another example here. Let's clean all this up. I got rid of the handle. It's okay. I don't know why I just won't draw another one. Resize. Let's turn it like this. And let's imagine we have a table. Like that. So what I'm showing here is what if we take that table and we tilt it on its side, and I'll draw little legs on this one. Well, the cup wants to slip. It wants to slip in this direction, parallel with the table surface. There will be some friction. There will be some friction that opposes that slipping, so it would be pushing this way and keeping it from slipping. But once again, it will be parallel with the surface that it's on. Okay, let's keep going. Tension force. So we will most often see it as F, capital F, subscript capital T. And you might see it like that, but this is just a force that is transmitted through a rope. Basically anything that's like a rope or a string. Um, okay, a cable. Okay, like a wire. Fine, a chain, a thread. You guys get the idea. So I usually show a picture of, um, a roll of tape that's attached to some string, or maybe a tire swing would be an example. There is a force that is transmitted through this rope that is pulling. And by the way, it can only pull. You can't push on a rope. So if your hand was here, you can't push with a downward force onto that tire swing. But the rope can pull the tire swing up, right? In fact, even if it's just stationary there, it is still pulling on the tire, pulling up. So that's, we would call the force transmitted through here a tension force. All right. The last one is an applied force. We will typically call it F1, and if we have two of them, we'll call the second one F2. We just give them a number. It's just a force by pushing or pulling. So sometimes when I say your hand is pushing on something, it's a weird looking hand, but the force that you're putting on it is an applied force. Just a force you might use. So this is just a quick introduction to some um, objects that we're going to be using. Not objects. I forgot what I was calling it earlier. It's kind of like a graphical tool that we use to show um, how to show forces on objects. Yeah, that's what it is. How to show the forces that are acting on objects. We call it a free body diagram. It's a representation of one body, so one object, with all the forces acting on it. All the forces acting on it. There's some rules for drawing that, but we'll address that after. So number one is a tire hangs motionless on a rope. So here's the tire, and it's motionless on, whoops, that was weird. Gosh, that's worse. Let me see. Here's the tire, and here's the rope holding it up. So just draw that as a solid rope. I'll just draw it like that. Let's just leave it like that. Now, when we represent it as a free body diagram, we don't really draw a picture of it. What we draw is, we typically just draw a dot that represents the tire, and we show all the forces on it. So all of these forces, not all of these forces, but some of these that apply to it. So does the tire have a gravitational force? Is it in contact with a surface? Again, is it in contact with the surface and it's prevented from slipping? Does it have a tension force from a rope? Does it have an applied force? So just going through that list, the tire is made of mass, and so it does have a gravitational force mg pulling down on the rope. I'm sorry, pulling down on the tire. And we represent the force with an arrow, where the arrow is pointed in the direction of the force because the gravitational force pulls down. And we represent the object with a dot. We need another force on there. Clearly there's a tension force pulling up. So we would call that Ft. So let's talk about the rules. You draw it as a dot or a box. I'm going to prefer dots for the time being. Forces must be drawn as an arrow pointing in the direction of that force. The rope can only pull, it cannot push, so it's pulling up. Gravity is pulling down. The forces must be labeled. That's what we showed, Ft and mg. Very clear what those forces are. The forces must be drawn pointing away from it. So don't do something like this. Don't do that. Don't put mg pointing towards the dot and Ft pointing towards the dot like that. They must be pointing away from it. And the last rule, arrows must be connected. So in other words, don't do this, which I see a lot of, just real messy kind of thing here. Let's not do that. That's number one. That's it. Number two, and I'm just drawing these just to illustrate it, like just to give you a visual. That's a stapler, clearly. Something like that anyway. Stapler sits at rest on a desk. Let's draw a dot for the stapler. Again, I always like to start with the gravitational force. It clearly has mass, so it has a force mg, gravitational force pulling it down towards the center of the Earth. It is on a surface. It is stationary, it's at rest. So it does have a contact force from the surface. Is it the normal force or is it a friction force? It's not a friction force, it's a normal force. So the table is pushing back up on the stapler with a force capital F subscript capital N. Number two. Number three, a wooden block is accelerated to the left on a lab table. So let's get rid of that. Here's a lab table, here's a block. It is accelerated to the left. So it has an acceleration. Sorry, that's a terrible arrow. It has an acceleration this way. That means that there needs to be a net force on this. So we'll draw a dot for the box, for the block, I mean. Now, again, starting with the obvious ones, it has gravitational force mg, it has mass, it's on a desk, so the desk is pushing back up on it with a normal force. So it's accelerated to the left. That means it must have a force, a net force, pushing it to the left. We'll just call that an applied force. Someone is probably pushing it. Now, they don't specify, but they didn't specify whether there's friction here or not. If we assume there's no friction, then our number three is done. If there's a little bit of friction on there, it would be opposing uh, how it's slipping there. So this would be a friction force. You must draw this less than F1 because there needs to be an overall force giving it an acceleration to the left. Okay, that's if it has some friction there. Whoops, always using the wrong one. So otherwise, we just leave it off, something like that. Okay, number four, an apple falls from a tree. There's no air resistance. So an apple is in free fall. There's only one force acting on the apple, which is the force of gravity. That's it. So that's kind of like a small introduction to free body diagrams and forces.